The problem statement from GATE Physics 2016 reads as follows. For the transistor shown in the figure, assume VBE equal to 0.7 volts and beta DC equal to 100. If V in equal to 5 volts, V out in volts is. This is a numerical answer type question and we are required to give our answer up to one decimal place. Before we start to solve any questions related to BJT, we ask ourselves a few things. First thing is, what is the nature? What type of BJT is it? Which BJT is it? NPN or PNP? If we note this symbol, the arrow is coming out of the emitter, and this means this is an NPN transistor. Second thing we ask is that which mode is this BJT operating in? Now note that if we are given VBE equal to 0.7, this means that your base emitter is forward bias. But the question does not say anything about the collector bias junction. So we'll assume that collector base is reverse bias. This means this mode is what we refer to as the forward active mode, and all the expressions where beta equal to IC upon IB, alpha equal to IC upon IE, all those expressions are valid only when the BJT is working in forward active mode. So we'll assume that the BJT is in fact working in forward active mode. Let's get a brief view into the working of an NPN BJT. On the top left here you have an unbiased NPN BJT, and if we bias it in this following manner, that NP is forward bias, base emitter is forward bias and base collector is reverse biased, you will get a large amount of electrons injected into the emitter. From the emitter to the base, a few will recombine, while the majority of them will get collected at the collector, and the currents will obviously be in the opposite direction of the flow of the current. And due to the application of bias, the Fermi levels shift accordingly, and you can see a large amount of electrons coming in, very few recombining, some holes also diffuse back, while the most of the electrons are collected. Mathematically, these can be represented as this first expression is nothing but the Kirchhoff's current law, IE equal to IC plus IB. Beta is the current gain, which is collector current over base current. Alpha is the collector current over the emitter current. Alpha is usually very close to unity. Now I just told you that here in this diagram is base emitter is forward bias, so collector base is reverse bias. However, there are four such configurations, and the most commonly used when I told you base collector reverse, base emitter forward, is we called it at the active or the forward active region, and you see is this region between the points B and C. This is the forward active region. The other region is forward for when both the PN junctions are forward bias, and this is called the saturation region. You can see in between the points A and B. Here the transistor is behaving more or less like a resistor, because you see I is direct proportional to V here. A third region is when the base collector is forward but the base emitter is reverse. This is called the reverse active, which is not shown here. Essentially the emitter and collector have reversed their roles. And finally, when both the PN junctions are reverse bias, and this is the cutoff region, which you can see here in this grayish region. We do not operate beyond VCE because that device tends to break down. So you can see after the point C, we do not usually operate. Now this is called the output characteristics. This is IC versus VCE, and you can see as we increase IB, IC increases, because we know that beta equal to IB upon IC. You know that beta equal to IC upon IB, so IC is nothing but beta IB, beta being a constant. As we increase the IB, IC should increase. Now let's I've just read on the circuit diagram with beta equal to 100, and we have to find the V out with V in equal to 5 volts. And now I've drawn the currents. The current IC is flowing into the collector and also through this resistor. Similarly, IB is flowing into the base and through this resistor of 200 kilo ohms, and IE is flowing out of the emitter and consequently through this resistor of 1 kilo ohms. Secondly, what I have done is that I have just given some node voltages. So this is VB, this is VE, and this is the collector, which is from where we are measuring the output voltage as V out. All these voltages are denoted in blue color. Now what I am going to do, I am going to apply KVL across the screen line. Now follow me carefully. We are going to apply the KVL across the screen line. Why I chose this screen line? Because I know what is the VBE drop here? So I can simply apply this here. This was given in the question, by the way, and in forward active we assume it to be 0.7 volts, sorry. So we'll just apply the KVL across the screen line and let's see what it comes to. So I'll write the KVL expression is V in minus IR, which in this case is IB times 200K minus VBE, note this drop we have reached here now, minus IE times 1K, which is equal to 0. This is the simple expression. So we know V in is 5, which was given, minus IB times 200K minus, I know VBE is 0.7 minus, and I also know I is nothing but beta plus 1 IB times 1K equal to 0. How does this come? We know that IE is IB plus IC if you apply KCL across the BJT, and this is IB, and IC we know is beta IB, so IE comes out to be beta plus 1 times IB. Simple expression, and I have just used this expression here. So let's keep IB terms on one side and the constants on the other. So we'll get IB times 200K plus beta plus 1 times 1K is equal to 5 minus 0.7 is 4.3. So I'll get IB into, so let's put beta equal to 100, so I'll get 200K plus 101K, which is equal to 4.3, and from this I'll get IB as 4.3 upon 301 kilo ohms, right? And we were required to find the V out. Now note that so we are required to find V out, right? So this is the second step. So V out is nothing but if we apply KVL simple here, so I can write, or we can apply Ohm's law across this 3 kilo ohms resistor. So I can write sorry, just ignore this. So it will be 10 minus V out is equal to IC times 3K. Simple. Ohm's law across this resistor, right? So now I'll write V out equal to 10 times 3K times IC, and I know IC is nothing but beta times IB, and beta is what, 100. So I'll just write the expression beta times IB, which is equal to 10 minus 3K times beta is 100. IB we calculated this value 4.3 upon 301K. So what's going to happen is I am just going to solve this expression here using my calculator. So the numerator is 300 times 4.3 divided by 301, which is nothing but 4.29. So it's 10 minus 4.29, and thus V out comes out to be 10 minus 4.29 is 5.71. So this comes out to be 5.71 volts. So we have calculated V out as 5.71 volts, right? Okay, so this is the V out, and this is what we are required to find out. So we can simply write V out as 5.71 volts. Okay, now we can also check one thing. So we calculated this value is 5.71 volts, right? We assume that this is reverse biased, so let's just check that. And we also calculated that this value, so IB we calculated, right? So IB was 4.3 upon 301K. So let's calculate this value. So that will be 4.3 divided by 301. So that will be around 14 microamps. So this is approximately 14 microamps. Okay. Thus, and this is 5 volts, right? So what will this node be? So this VB will be equal to 5 minus 14 microamps times 200K. So this will come out to be, I'm just calculating it for you. So this will come out to be, just a second. So this is coming out to be 2.14 volts. Okay, so this node is at 2.14 volts. Now we can clearly see that this is reverse bias. Note that this is the NP, this is NPN trans. So this is N and this is P. So N terminal is at a higher potential as compared to the P terminal. So this junction is clearly reverse bias. So, and we assume that, right, that collector bias should be reversed, and it is coming out to be reversed because collector is at 5.71 volts and base is as 2.14 volts. So this is clearly a reverse bias, so our assumption is correct, and we calculated using this assumption of forward active mode that the value of V out is 5.71 volts. And this is one decimal place, so we can simply write it as 5.7. Note one decimal place, so 5.7 is the answer. Thank you for listening.